All right, good evening. My name is Cheyenne Smart, and I will be talking about a convenient method for the removal of tetrabutyl ammonium salts from distillation reactions. So let's get started. So the first slide we have is the scale and optimization. So the first question we come across for this section is how large of a scale can this reaction be run safely? So this experiment was done on the largest possible scale, and the experiment was done also on half the scale, which we'll talk more into detail about that later into the presentation. Is it expensive? Let me see if I can move this here. Okay, great. Yeah, I'm gonna move this. So the based off the journal, the experiment is relatively inexpensive. Um, the experiment is very cheap. The most expensive reagent used in the experiment was the Dowex, which when I did a little bit of research, it prices at $262.50 per gram, which is kind of expensive because a gram is about a handful. Um, and then I also looked at different reagents that was used as well, the prices for that. So the methanol in the experiment was about 70 cents per gallon. The THF was $83 per bottle, and then the T bath was I seen $18.50. So it's not as much as the Dowex, but it's still pretty inexpensive for the experiment that was carried out in this journal entry. Okay, the next one is the check-in process. Let me move this here. Okay. So, the check-in process, as far as that goes, the checkers carefully checked each procedure and all characterization data. The checkers ran the experiment for a second time on half the scale. When doing so, the checkers omitted a step of the experiment, which I'll point out once I go through the procedure. This step consists of submerging the dram vial holding the oil in a dry ice acetone bath and drying it for an hour under high vacuum before drying it at 20 degrees Celsius. That's a mouthful, but I'll go more into detail about it when we'll go through the procedure. The first trial run had a 88% yield and a 98% purity, and then the second trial run had, which was the half the scale. That one had an 80% yield and a 90% purity. Okay, let's see here. Okay, so as far as the reaction apparatus, so for this experiment, the initial setup of the apparatus consists of a tough Teflon coated magnetic stir bar, which was three by 1.5 centimeters, which is a football shaped magnetic stir bar. It was equipped with a rubber septum, and it was also equipped with a nitrogen inlet, which is used for nitrogen purging to effectively displace moisture and oxygen and creates a more stable climate for the apparatus. So as you can see, let me use this here. This is so tricky. All right, so as you can see here, this is image A. So this is the initial setup with the addition of T-bath, or the after the addition of T-bath. Excuse me. And this here, as you can see, is the nitrogen inlet. In here, you can see the magnetic stir bar, which is used for stirring, and then the rubber septum, and is held up by a glass or a clamp. Um, then we have image B, which you can see here. This is after the addition of the Dowex ion exchange. And here you can see it stirring, which I believe it was stirring at 300 RPM. I could be completely wrong, but I'll go into it once I go into the procedure. So here I have a chart with all the reagents and starting materials. Um, so I just want to point out that some of them are the reagents that was in the mechanism, that was part of the mechanism, which is the T bath. This here's part of the mechanism. THF is part of the mechanism. The Dowex, let me move this over. You can see there's nothing here. The Dowex is part of the mechanism. The methanol was part of the mechanism, and the calcium carbonate was part of the mechanism, which I'll show into detail once I get to that part. So you can see that the 4-bromophenol, the mass of that used was 4.5 grams, 16 millimoles, and the equivalency was 1. For the tetrahydrofuran, or known as THF, the volume was 30 milliliters. The tetrabutylammonium fluoride solution, the millimoles was 19. The volume was also 19. The equivalency is 1.2, and the concentration was 1. For calcium carbonate, the calcium carbonate was it weighed 8.2 grams. The millimoles was 82 millimoles, and the equivalency is 5.3. Also, I forgot to mention that for the 4-bromo terbutyl, that was part of the starting materials in the experiment. So it wasn't part of the mechanism, but it was used in the beginning of the procedure. So I wanted to include that in the chart to just show like what was used in the very beginning and what was provided with the different mass, equivalency, volume, etc. So we can just clear that. Let's go to the next one. So this is a continuation. So was there any special precautions of the reagents required? So I just want to mention that phenol was used, and it is a very weak acid, but it can cause harm if not careful. To ensure this from not happening, it's best to wear gloves in the lab, which is already a given. When you're in lab, you would wear the proper PPE, such as the lab coat, the gloves, and the goggles, so that way you don't, have any irritation or anything. So, like I have listed here, it can cause irritation to the skin, nose, throat, and even the nervous system. And it's best to wear gloves to prevent any irritation if it was to get on your skin. Uh, so, as far as the limiting and excess reagents, so the experiment's limiting reagent is the 4-bromophenol terbutyl. Sorry, excuse me. And we know this because if we go back, the equivalency is a 1. So based off the equivalency is what the limiting reagent is. And then why is the excess necessary? So the excess is necessary um, because it's to ensure that the reactant is fully reacts with the limiting reagent. So you want to have just enough material in order for the experiment to be completed and to be sure that it does react with whatever the limiting reagent is. Okay, so this is the start of the reaction procedure. So I'll go into that. I think that's everything I wanted to mention. Um, Also wanted to mention that I wanted to go back as well that the purity of all starting materials and reagents are not mentioned until the end of the experiment. when the crystalline white solid was collected at the end of the experiment. Um, so, in other words, I wanted to mention that because the purity wasn't really, like I said, it wasn't mentioned until the end when the whole entire experiment was completed. And that's when I mentioned before that the purity of both the full reaction and the half scale reaction um, were around 98%. So as far as the knowing what each material's purity was, it wasn't necessarily mentioned in the journal. So I just wanted to make note of that. Also, I have a list of where every material reagent was bought. So the 4-bromophenol was purchased from the Sigma Aldrich Corp and was used as received. The tetrahydrofuran, which is the THF, was purchased from Fisher Scientific and used as received. The submitters passed it through an activated alumina column before use. The tetrabutyl ammonium fluoride, which was purchased from the Sigma Aldrich Corporation and was used as received as well. The calcium carbonate was purchased from the Fisher Scientific and used as received. The Dowex mesh ion exchange resin was purchased from Sigma Aldrich Corporation and was used as received. The methanol was purchased from Fisher Scientific and used as received. The cellite was purchased from Fisher Scientific and used as received. Um, the reaction flask, I also want to mention that the reaction flask was rinsed 3 times with methanol to achieve a quantitative transfer of the contents of the reaction flask through a cellite pad. And then the Cilia flask was purchased from Cycle and used as received. The methylene chloride was purchased from Fisher Scientific and used as received. The pentane was purchased from Honeywell and used as received. The submitters used hexane instead of pentane. Honestly, I'm looking. So okay, so I think I made a mistake. So the purity was. I'm assuming it was mentioned because it's numbers next to it. So I'm assuming the numbers here is the purity of each material. So the purity, if I'm not mistaken, the purity for the 4 bromo was 90%, 97%. The THF was 99.9% pure. The calcium carbonate was 99% pure. The methanol was 99.8% pure. Um, and the methylene chloride was 99.5% pure. Pentane, 98% pure, was purchased from the Honeywell and used as received. The submitters used hexanes instead of pentane, and then the diethyl ether was 99% pure and was purchased from the Fisher Scientific and used as received. So, okay, yeah, I made a mistake. I'm sorry. Um, so yeah, just based off of this list uh, that I have here, these are all the materials that were used, and this is basically a description of it. Either like, for example, the flask was rinsed 3 times with methanol to be sure of any cross contamination or anything, whereas everything else was used as received. So is like that is the purity of every starting material and reagent that was used in the experiment. Um, so yeah, I just want to just clear up that, and I made a mistake. Sorry, but yeah, just wanted to mention that. So let's move on. So let's go to the first thing. Here we have the reaction procedure. Okay. So let's use this. So the first step is to equip A single-necked 20/40 joint 250 milliliter round bottom flask with a Teflon coated magnetic stir bar, which we've mentioned already earlier before of the setup of the apparatus. Then we want to flame dry the apparatus under reduced pressure and cool to 23 degrees Celsius under an atmosphere of nitrogen. After doing so, equip the flask with a rubber septum and then place under positive pressure of nitrogen using a nitrogen inlet. And this is where the nitrogen inlet comes into play to help with that, the pressure of the nitrogen to manage that. Like we said earlier, the inlet's purpose is to be used for nitrogen purging. The next step is to add the 4-bromophenol terbutyl dimethylsilane, mouthful, and then I add the which we already have in the chart from before, the scale via syringe to the flask. Then we want to add THF at 23 degrees Celsius to the flask via syringe and stir at 300 RPM. So remember the picture, I just want to go back real quick. That picture that I was showing, so this one, picture B, I just want to clarify that that was actually stirring at 300 RPM. So we can go back. I just wanted to show that. After 1 minute of stirring, a 19 milliliter tetrabutyl ammonium fluoride solution via syringe dropwise over 5 minutes. Then allow reaction mixture to stir at 300 RPM at 23 degrees Celsius for 30 minutes. Once we do that, we remove the rubber septum and then add in 1 portion of calcium carbonate, followed by the Dowex, which the Dowex is used to clean up everything, in 2 equal portions using a funnel to assist with the addition. Okay, step 9. Add methanol 60 milliliters to the reaction mixture. Then place the rubber septum, including the nitrogen inlet, and stir the suspension for 1 hour at 23 degrees Celsius at 900 RPM. Filter the resulting mixture through a wetted cellulite pad. And it was 28 grams wetted with methanol, 7 by 4 centimeters in a 150 milliliter medium porosity fritted Buchner funnel into a 1 liter round bottom flask, using methanol. Using a rotary evaporation at lower pressure concentration, concentrate the filtrate to yield the biphasic mixture of a colorless liquid and a yellow liquid. So this is what we see here. I just wanted to add the picture from the experiment, the filtration apparatus, where the concentrate, or I'm sorry, the mixture was then filtrated here into the flask here. Okay, step 12. Charge the 1 milliliter 1 liter round bottom flask with silica gel. So you can see this is where's what's going on here in image A. I'm gonna add my colors. Suspend the crude material and silica gel in the methyl chloride and concentrate under reduced pressure until a fine powder results. Add the product absorbed silica to a column, which is seen here in image B, which is prepared using silica gel that is wetted in pentane. Then it's going to be eluted to a column which is with 19 to 1 pentane diethyl ether, followed by a 9 to 1 pentane diethyl ether, 1 liter and followed by a 4-to-1 pentane diethyl ether. So they wanted to be thorough, as you can see in this experiment. Step 16, collect the product in a 55 milliliter culture tube or culture tubes and elute the desired product in fractions 35 to 66. Then pool and concentrate the fractions under reduced pressure, and then transfer the resulting yellow oil into an 8-dram vial using diethyl ether and concentrate it under the reduced pressure. And then the last step is to dry the resulting oil under high vacuum at 23 degrees Celsius for 18 hours to yield a crystalline white solid. And here's what we have here. This is the isolated 4-bromophenol, which is what we wanted at the end of the experiment, which they received at the end of the experiment. This is the last bit of it. So they did use a TLC analysis. Um, so the reaction is monitored with a TLC plate, and the order of addition is very important. Just to go back on the procedure, the order of addition is very important to follow so that the experiment can carry out the way it's supposed to. Without the proper order, the objective of the experiment may not be achievable. So I just wanted to mention that because you have a goal in the beginning of the experiment and you want to be able to reach that goal. So it's best to be able to do the steps in an orderly fashion so that way you can receive or you can arrive to your desired results. So back to the TLC, I just wanted to kind of mention this here. So as you can see, this is the TLC plate. And here we have a TLC of the crude reaction mixture after 30 minutes. So the TLC analysis is performed to track the reaction's development on silica gel with a 9-to-1 hexane, and then the hexane and the ETOAC were purchased and utilized by a supplier by Fisher, which I'm pretty sure I mentioned before with the list. The plate is visualized under a UV light, as we can see here. This is how we could tell where each material traveled or how far the material traveled. So the SM is the starting material and the RF value is 0.8. Then the CS is the cold spot of the starting material and reaction mixture and the reaction. Oh, I made a mistake here. It's reaction mixture. And then the RXN is the reaction mixture, which is the RF value of 0.2. So this is the starting material. This is how far it traveled. Then the CS is the mixture of both the starting material and the reaction mixture. And then the this here is the reaction mixture, and that's how far it went. Reaction workup had a number of things that was needed to be mentioned. So the first thing was the quenching of the reaction. I just wanted just to say that that all of these steps were from the actual the experiment and was mentioned in the procedure, but this is how they did the reaction workup. So for the quenching of the reaction, so we've mentioned before, to the reaction mixture is then added the methanol, and the rubber septum is replaced using a nitrogen inlet, and the suspension is stirred for an hour at 23 degrees Celsius at 900 RPM. So this is the way that the experiment was hydrated, and it was hydrated with methanol. And methanol was added into the reaction mixture. Then the next part is the extraction process. So as far as the extraction goes, um, the resulting mixture is then filtered through the wetted cellulite pad, that was wetted with methanol, and it was filtered into a 150 milliliter medium porosity fritted Buchner funnel into a 1 liter round bottom flask using methanol as a eluent. Um, so this extraction was performed once, and I have everything here listed as far as the extraction procedure. The mixture was filtered through so that way the wanted material was collected. Okay, let's clear that. Move on. Then the next part is the concentration. So the filtrate is then concentrated by a rotary evaporation under reduced pressure to yield a biphasic mixture of a colorless liquid and a yellow liquid. So just to note that the yellow liquid is the crude material that we do want at the end, which is the let me go back, which is the material that we want at the end. So yeah, I just wanted to say that that's what we have wanted, which is the yellow material. Oh, no, moving on too fast. Okay, so yes, the yellow material is what we want at the end. Um, so yeah, and yeah, the round bottom flask is charged with silica gel. And then for the drying reagents, the 1 liter round bottom flask is then charged with silica gel, and the crude material and silica gel are suspended in methylene chloride and concentrated under reduced pressure until a fine powder results. So we want to see a powder form in order to have the material to be able to test the purity and the percent yield at the. That's basically the gist of the reaction workup. So let's move on. This is almost done. So purification. Um, so for the distillation apparatus, the product absorbed silica and then was added to a column, which was prepared using silica gel that is wetted with pentane. The column is then eluted with a 9-to-1 pentane diethyl ether, followed by a 9-to-1 pentane diethyl ether, followed by a 4-to-1 pentane diethyl ether. So we've already mentioned that before in the procedure. And then the chromatographic purification. This is when the product was collected in a 55 milliliter culture tube, or culture tubes. I keep saying tube, is more than one tube. And desired product elutes in fractions of 35 to 66. These fractions are pooled and concentrated under reduced pressure, and then the resulting yellow oil is then transferred to an 8-dram vial using diethyl ether and concentrated under reduced pressure. And then the recrystallation process, this is what we want to receive the product towards the end, or try to isolate. The whole procedure is to try to isolate the product at the end. So the remaining oil is then dried under a high vacuum at 23 degrees Celsius for 18 hours to yield a crystalline white solid, which we see that the white solid weighed 2.44 grams. Uh, the percent yield is 88%, and then the purity is 98%, which is a um, really good numbers. Okay, then here we have the proof of the purity. So for this particular experiment, you would think that the TLC was the proof of purity, but that was more so to monitor each reagent. Um, but for this one, this was used, or the proof of purity was done by a NMR. Um, so as you can see here in both charts, We have where it calculated the percentage of purity and it came close to together, which I've mentioned before and I wanted to mention again that the experiment was done twice. So the one with the procedure, which I've read the procedure, that was done on the full scale, and then the experiment was done again. Here I'm marking the NMR for the one that was done on half the scale. That was done again by the checkers of this experiment, to make sure, like, this was carried out correctly and to prove the experiment does actually work. So you can see that they both got to a 98% purity, which is actually really good. So yeah, this is just to prove that, the experiment was, you know, done correctly and to prove that they had the right material. And you can see, like, on the NMR, the different peaks was relatively the same. You can see this one is shorter than this one. So just want to mention again that it is very important to wear the proper PPE in lab. And without the proper PPE, the person who's doing the experiment could be exposed to hazardous chemicals used in the lab and can be put at risk to their health and safety, which we do not want in any experiment. So it's good to wear gloves, goggles, and a lab coat. And also, there's other things that you could do as well to be safe, such as, tying away long hair, not wearing any jewelry that's dangling, um, and just wearing the proper clothes or attire to the lab as well. Clothes, shoes. You don't want any sandals at the lab. You just want to make sure that everyone is safe. And is the reaction more dangerous than most reaction? Um, so I'm gonna get into it to the next slide, but I just want to briefly mention that the experiment didn't really mention any materials used to be very hazardous. However, I did mention in the beginning that the phenol could be acidic and with careless with it being used carelessly, it can irritate the skin, and we don't want that, obviously. So as long as the lab precautions, safety lab precautions are taken, everything should be fine as far as the safety measures of the experiment. So yeah, the reaction is fairly safe. And then the lab did mention a safety disclosure, and this is basically it, just saying that, just out of the safety of everyone doing these techniques, just to be sure, like, everything is done the correct way and safely, done with all the different proper PPE, things like that. So this is the discussion part of the experiment to show a drawn out way of how the experiment is basically received to its conclusion. So we see here that the experiment starts off with 4-bromophenoxy. Well, this is the tert-butyl. This is what we started off with, and we want to we wanted to isolate the 4-bromophenol. This is what we want. So let me get my pen. So this is where we start off, and we would like to isolate to this. So how do we get to here? Good question. So here are the starting materials, which I've said also in the beginning when I was reading off the table that these are the starting materials that were used, and then there was one other thing that was used in the beginning of the experiment. But for the most part, this is what was used as reagents for this experiment carried out. So with these here, it goes into this, which is the uh, 4-bromophenoxyterbutyl dimethylsilane. And here we have the tetrabutyl ammonium fluoride, which is also referred to as T-bath. So the fluoride here that comes from this whole thing attacks the silicon here and makes the silicon detach from the oxygen here. So I'm gonna clear that off. So also, I just want to mention as well that water is also present here in the in tea bath. So that's like really hard to get rid of. So I just wanted to mention that. So that's just there to just just to mentally note that. Um, so anyway, so the fluorine attacks the silicon. The silicon is a positive charge, and I want to say the valence electrons for silicon is 4. So it has a positive charge, so positive and negative is, always attract. So this wants to attack that. And with that being done here, and the silicon is gone, now the O has a negative charge. And here's some hydrogen here that also reacts to here that comes from the water. Um, and with that, it results to byproducts here. So it results to byproducts, and this is the resultant from it reacting with the water from the tea bath. Just want to write that out just to be sure that we know that it's byproducts. So this is the byproducts, which is the tert butyl dimethyl silanol, and then the terbutyl fluoro dimethylsilane. So we don't want this stuff. This is just the kids that couldn't come that couldn't come over to the house because they're in trouble. No, we don't want them. We don't want them at all. This is the vegetables that the kids don't want. We don't want these vegetables. We don't want this broccoli and this spinach. Mm-mm. We want the candy, which we also have here. Trying to draw it to the best of my ability. We want that to be isolated, which is what we want to get rid of this here, which is the 4-bromophenol. So with that being said, this is the ending product, and from the OTBS and results into a alcohol. So that's all we want. It's other stuff here, like we mentioned. Sorry. Um, yeah, that's what we wanted towards the end. And like I said, everything is pretty cheap to do this experiment. So yeah, and that's about it. And these are our authors. The first author here is Luca McDermott. Sorry. Um, Luca received his BS in biochem from Tufts University. In 2020, he began graduate studies at the University of California in Los Angeles, where he was a second-year graduate student. Good for him. Students. Studies are primarily focused to total synthesis. Then we have here Dominic Witkowski. Dominic received his BA in Chem from Boston University. In 2020, he carried out research at Boston University and most of the University of California, Los Angeles as a second-year graduate student. Studies primarily focus on developing synthetic methods utilizing strain cycle amines. These are some very smart people. So yeah, and then we have the professor of chemistry, which I'm gonna assume that he was the leader of this whole thing because he is the professor, and most of everybody else is students. So the professor here, Professor Neil Garg. Professor Garg is a professor of chem, and he is the Kenneth N. Trueblood Endowed Chair at the University of California in Los Angeles. And his lab creates novel synthetic strategies and methodologies to enable the total synthesis of complex bioactive molecules. Then we have Philip, and I'm gonna put S here because I don't want to butcher his last name, but he conducted his BSc and MSc studies at the University of Munich. I hope I pronounced that right. And then he finished his MSc degree with a research stay in a group working in nickel catalysis. The studies primarily focused on total synthesis, on developing new methodologies in the area of amide activation. Last but not least, we have one more person. So, Mr. Kaiser received his PhD of University in Vienna and returned to Vienna at 2020 to assume a position as senior scientist in the MELID group. The current research focuses on chemistry of destabilized carbocations and related high energy intermediates. So, thank you so much for sticking around, and I hope that this is a good experiment and a good presentation, and I hope you enjoy. Thank you.